It is on right now. Okay, hello everyone. Welcome to the last session of the Eurocrypt, one of the two last sessions on non-malleable commitments and obfuscation. So we have the first paper and presentation on non-uniform security for black box non-interactive CCA commitments by Rashid Garg, Dakshita Khurana, George Liu, and Brent Waters, and Rashid will give the talk.
Hi everyone, I am Rashid Garg, and today I'm going to present our work, Non-Uniform Security for Black Box Non-Interactive CCA Commitments. It's a lot of words, and I'll break down each of them while I'm giving the talk. And this is joint work with Dakshita Khurana, George Liu, and Brent Waters. Let's start with what are commitments. Commitments are a two-round protocol between a two-phase protocol between two parties, Alice and Bob. The first phase is called the commit phase, where Alice has a message M that she wants to commit to Bob. So she puts her message inside this lockbox, so it's a physical world analogy, and she sends this message to Bob. So Bob has this message, but he cannot read it because it's inside this lockbox. So the second phase is called the open phase, where Alice has this key, and then she sends it to Bob, and Bob opens the message and reads it. So there are two guarantees that we want. We want hiding, where in the commit phase, the message should be hidden to Bob. And binding, which says that Alice should not be able to open to a different message than what she originally intended. This is applicable in, this is useful in coin flipping, auctions, and multi-party computation in general. Let's look at auctions. So imagine you have three parties and all want to bid for some auctions. So in this setting, all these parties commit to some art piece, which is like $50, $100, $75. And let's say Mallory wants, and she really wants to win the auction, and she comes in, and she knows that like the party in the middle might be the one who might be bidding highest. So she does not know what the party in the middle's commitment is, but somehow if she is able to mull the commitment into a related commitment, in this case one more, she'll be able to win the auction with more information that she should have. So this is undesirable, and such adversaries we'll call non-malleable adversaries. So there's been a lot of work in building non-malleable commitments in literature. And we started with logarithmic round protocol from the seminal work of DDN in 1991, and we built this from one-way functions. And since then, we've had plenty of results, where we've gotten 3-round protocols, 2-round protocols, and eventually non-interactive protocols. So in non-interactive protocols, there is only a single message sent from Alice to Bob in the commit phase and even in the open phase. So there is no setup, and there's only a single round of interaction. And this is going to be the focus of this particular talk. So how do we build these non-malleable commitments in this non-interactive world? We start with any set of favorite cryptographic assumptions that you might have, and we build this intermediate primitive, which I'll call tag commitments. So all these prior works follow this template, that they first build this intermediate primitive, tag commitments, and this captures most of the flavor of non-malleability. And then once we've built this tag commitments, we do a transformation to get the full notion of non-malleable commitments. So I have an asterisk here. So the caveat is that you need a one-time signature scheme, which exists from one-way function, so it's not that bad. But the caveat, the one that I really want to point out, is for this tag commitment scheme, you need exponentially many tags for this transformation to work. And let me tell you what these tag commitments are. So these tag, in a tag commitment, your algorithm is slightly different than what I originally showed you. So instead of a commit taking a message with some randomness, it also takes this tag. And similarly, open also takes a tag value. And correctness says that once these two tags match, you should be able to open the message. And you have the same hiding and binding guarantees, where commit says that it should hide the message M, and binding says that you should not be able to open to a different message. And in this talk, we'll only focus on this notion of perfect binding, which means that there will never exist another opening. So the non-malleable adversaries in this man in the middle, in this scenario, is a man in the middle where it's reading messages on the left and trying to commit something on the right to Bob. So because in this tag notion, now while they're committing, Alice's tag is going to be attached in this commitment message. And what we want is like we shouldn't allow some party to commit to 100 to like let's say 101. So basically, the important thing is if we're committing on the left to a message M and committing on the right to a message M dash, then M dash must not be related to M whenever this challenge tag is different. So whenever tag is not equal to tag star, which is important, this guarantee should hold. So it captures most of the non-malleability property. So how do you build these tag commitments? You start with these assumptions, and you end up building first a scheme for C log lambda many tags. And then you do a tag amplification procedure, and you build it for exponentially many tags, which is 2 to the power lambda many tags. So this tag amplification procedure, which exists for all these schemes, is very important. So how do you do this very important tag amplification procedure? Most of the prior works, they use either non-interactive witness indistinguishability proofs or sub-exponential I/O. So you don't need to know what NIVs are, but the point is that using NIVs and I/O makes you use non-black box use of crypto, and this leads to inefficiency because you actually need to write the code, and it's much more complicated to implement. And additionally, NIVs and I/O you only know from a very specific set of assumptions. And NIVs you know from bilinear maps or de-randomization assumption, and bilinear maps are broken, are not secure post-quantumly. So you really want to expand on the number of assumptions you know while making black box use of crypto. In an earlier work we had in 2021 with the same set of authors, we actually showed how to remove NIVs and I/O, but the caveat there was that we were only able to show security for uniform adversaries. So let me just explain why in our work we're going to try to get security against non-uniform adversaries. And why do we want that? Non-uniform adversaries is a stronger model of computation, of adversarial security, where the adversary might have access to some advice string, and still it's required that the security should hold. And if we prove security against non-uniform adversaries, we'll get a stronger composition theorem, because when you're going to use these non-malleable commitments inside your favorite MPC protocol, you're going to get a better guarantee on your schemes. Secondly, sometimes when building these MPC protocols, you might require non-malleability against non-uniform adversaries for the security proof to work out. So just to build the scheme, you might need security against non-uniform adversaries. And just to reiterate, so we are in this non-interactive setting where we are making black box use of crypto, and there is no setup, no CRS, no random oracle. OK, so great. Now we're on our result. So we show how to build non-interactive, non-malleable commitments, specifically a tag amplification procedure, where we start from like log lambda many tags, and we amplify it to 2 to the power lambda many tags, and we prove security against non-uniform adversaries. And we make black box use of crypto, and we avoid NIVs and I/O. And you might ask me, OK, this is non-malleable commitments. I might not be familiar with it, and there's like huge literature behind it. So I additionally want you to see our result as a way of doing consistency checks. So in like many MPC protocols, you often require, like when we're dealing with malicious adversaries, that we prove some sort of computation check and make sure that the adversary is actually doing the computation correctly. And I see as our technique being more applicable to even other scenarios where you can do and set up these sort of consistency checks. And it might be applicable in other areas as well. So great, now that I've convinced you that even if you don't know non-malleable commitments, like you should be reading our paper, let me make your job easier and describe the main techniques. So in our paper, when we're considering non-malleable adversaries, we are going to model them as CCA, in the CCA experiment. CCA is chosen ciphertext security, and if you're familiar with chosen ciphertext security in the encryption setting, this looks very similar. So in this setting, the adversary is going to have access to this decommitment oracle, or I'm going to call this the val oracle, which is basically functioning like a decryption oracle. So this val oracle gets a commitment C, and then it gets the underlying message inside the commitment. So in the experiment, and this val oracle might be efficient, so you can imagine the underlying implementation of the val oracle might be like a very inefficient brute force opening. So the experiment, the adversary sends like a challenge tag star, which it wants to win the security game on. It gets to ask these val oracle queries, and notice that you're only opening if the challenge commitment is different. So if it asks the commitment, if it asks you to brute force open this val oracle on a different tag, only then you open. And then the adversary sends 2 messages, m*0, m*1, gets a commitment on one of them, and again makes oracle queries, and in the end, the adversary wins the game if it is able to guess correctly. So it's the classic CCA experiment game. Great. Now that we've sort of described what the main security game is, let me show you the construction. So there's a tag amplification procedure where you want to go from log lambda many tags to 2 to the power lambda many tags. And we're going to do it in stages. We're going to do an exponentiation once, and so we get to log lambda, and then we're going to do it two more times to get lambda, and finally 2 to the lambda. So how to do it? So imagine for this toy setting, like let's say you have this big tag commitment where this tag is 5 bits. So the space of your possible tags is 2 to the power 5, 32. And you want to use a smaller tag scheme to build this. So in this, I'm going to have 10, the smaller space is going to be 10 many tags long, where the first position is either a 0 or 1, and then it's 5 possible values for the second. So how to build this? I'm going to do a standard bit decomposition thing, where I'm going to encode my big tag into these small tags. And so basically here, the position 1 has bit 1, position 2 has bit 1, position 3 has bit 0, and basically I'm encoding this in the small tags. So my amplification procedure is basically going to be all these commitments on these small tags. But notice that I need to make sure that the adversary or the committer is not doing something funny. So I actually need to introduce a proof of consistency to make sure that all these messages, all these commitments are on the same underlying message. And this you can use NIZK proofs or any sort of proof of consistency, but you don't want to use NIZK to do this because NIZKs don't exist without setup. So, and we're really in this non-interactive setting where we want no setup. So prior VOOCs use NIVs, or which are weaker primitive, or we use hinting PRGs and other techniques. But the exact details of how we do these consistency check is not important for this high-level explanation of the talk. But only note that there is some sort of consistency check involved here. So we have this challenge commitment, and we have this proof of consistency. How does the security proof look? So the security proof, to describe the security proof, I have to describe to you what the val oracle does. So the val oracle is a brute force sort of oracle which opens it. So in this setting, the val oracle, what it can do is it first checks if the proof is consistent. And once it's checked that the proof is consistent, it can sort of open the underlying commitment on any of the small val oracles. So I'm defining this val oracle based on this smaller val oracle. OK, so my main step of the proof would be to change how I set up my, how to respond this val oracle queries. So earlier, this val oracle queries was opening it under the first tag, tag 1. So when it gets this big tag, it can, it's a bit decomposition. So you're only going to pick the first small tag, first position, and going to open it under that. But I could have chosen to open it under any commitment that I wanted. So that's going to be my first hybrid change. Once I get a val oracle query, I'm going to open it under a different tag, tag J, where tag J is different from the challenge commitment. So notice that whenever adversary queries in the security game, it's going to query on a tag which is different than the challenge tag. And because it's different than the challenge tag, there's always going to be one position which is going to be different. And because there's one position which is different, now I can go in a security game where whenever I'm opening using my val oracle, I'm always differing at like one. I'm never opening under the challenge tag. So I'm never going to open on tag star 1, tag star 2, tag star 3. I'm always going to be opening under different tags. And once I've made this change, then I can change the underlying messages to 0 using the security of the underlying non-malleable commitment scheme. And once this is done, I have removed all information about the message, and my scheme is secure. So this is the high-level template. Basically, there's a CCA game on big tag. Then you do change the val oracle to open to a different tag than the challenge tag. And once you've set it up in such a way, you can use the security of the underlying non-malleable commitment scheme. So in our paper in 2021, we used the first hybrid change. The main security component that we used was a collision-resistant hash function. And these collision-resistant hash functions, you can imagine them as like SHA-256 or something. So basically, it is a compressing function, and it's hard for an adversary to find two inputs which hash to the same value. And it's called keyless because we don't want any setup. And there is no setup for like a SHA-256. But note that this sort of primitive only makes sense in the uniform setting. In the non-uniform setting, it does not really make sense, because if you have advice and it is a compressing function, there always exists some two values which hash to the same thing. So if there exist two values that hash to the same thing, the adversary can always find them. So there is a how to do this in this non-uniform setting. So there's a primitive of non-uniform keyless collision-resistant hash function, which was introduced by Bitansky, Kalai, and Paneth in 2018, and Bitansky, Lin in 2018, which is a very natural extension of this notion. So imagine that now the adversary has this advice where originally we said that it's hard to find x1 and x2, which hash the same value. Now we can ask that, let's say if the adversary has s bits of advice, then it's hard to find polynomially of many s collisions. So like you can imagine s square many collisions or 2s many collisions, where the number of collisions that you want is more than the number of advice that you have. And this sort of primitive sort of makes sense in this non-uniform setting. Now the question is, can we use this new primitive to actually do the reduction from our old tag amplification procedure? And here I want to make note that the way the original reduction worked was if you could find a special commitment C star where the two oracles were sort of outputting something different, then you could use this to build a reduction to show a collision, hash function collision. But this is not possible in the uniform setting, because in the uniform setting, given advice, you'll always be able to find collisions. So how to set up this reduction? And the main idea here is to set up this reduction. If you find some commitments which are differing, I want to sort of link them with the corresponding collisions in a one-to-one injective way. And once I link them in a one-to-one injective way, I'll be able to set up my reduction so that once I have these special commitments which are differing, you can output the collisions correspondingly. And this injectivity is important, because if this didn't exist, then there could be exponentially many, even given constant number of collisions, there could be exponentially many of these bad commitments. So to set up an efficient relationship between given your advice and the number of collisions that you output, you need this sort of injectivity property. And this is the main core technique that we introduced in our paper. So just a brief list of ingredients. In our old work, we used hinting PRG and keyless collision-resistant hash function. Hinting PRGs are like special PRGs where you're expanding your number of bits. So imagine you have a seed S, and you're outputting a bigger string on the right. You don't need to know what exact special property is there. But in our work, we use hinting PRGs with injective extension, where along with this big seed, now you output some injective information. And you use this to link between the special bad commitments where val oracle differs to the exact collisions between the hash function. And these you can build from CDH or LWE. And the second primitive is the keyless collision-resistant hash function, which has this property that given S bits of advice, you should not be output more collisions. So I'll just leave the results side on the page where we built this non-interactive, non-malleable commitments where we did a tag amplification procedure and proved security against non-uniform adversaries using these two objects. So thank you.
Thank you very much for the great talk. Any questions? We have time for a question or two. So maybe I ask one. So you eventually get your construction based on, say, LWE. Mm-hmm. If you want to get it from simpler assumptions, what are the strongest barriers there?
Yeah, so there are multiple. So I have like an open question slide. Let me. So there are different axes of like open like assumptions that you can remove. So there's the keyless collision-resistant hash function. Right now we have like an dependence where we are asking that if you have S advice, you should not be able to output 2S many collisions. You could ask for a stronger assumption where you're saying S advice and S square many collision or S cube many collision. You can improve on that. And there was this work, so this line of work started by Coppola and Waters in 2019, where they first showed CCA security of public key encryption. And then they were able to get security instead of this hinting PRGs or this LWCDH from like injective trapdoor functions, which were a weaker primitive. So maybe even those techniques can be applicable. So there's both lines of like ingredients which maybe you can improve on.
Great, thank you for also using this slide. Yeah, nice, thank you.
Thank you.
Any other questions, or we can move to the next talk? Let's thanks the speaker again.
one. No, but the first one was.
It was just on the last.
Oh, okay, sorry.
I think we just go to the first page. Just
I think it's 1 minute.
go next year.
Sorry.
Okay. All right.
Okay, maybe I can introduce it quickly. The talk is polynomial time cryptanalysis of the subspace flooding assumption for post-quantum I/O by Ayush Jain, Huijia Lin, Paul Lu, and Amit Sahai, and Paul will give the talk.
Great. All right. Hi, I'm Paul Lu, and this is joint work with my co-authors Ayush Jain, Rachel Lin, and Amit Sahai. And right. Okay. So what is I/O? I/O takes a circuit C0 and produces a obfuscated C0 hat with exactly the same input-output functionality. And the security guarantee you get from I/O is if I take two circuits C0, C1 that are functionally equivalent and of the same size, then the obfuscated I/O obfuscated versions of these circuits, C0 hat and C1 hat, are computationally indistinguishable. And I/O sits as a central hub in cryptography. Namely, I/O implies both core primitives, as you see on the left-hand side, and new world primitives on the right-hand side. And for many of these new world primitives, we actually don't know how to achieve them without I/O. So I/O sits really as a central player in cryptography. And more so, recent work by Jain, Lin, Luo, and Wicks in 2022 show that in this pseudo-random oracle model, you can take I/O and actually build ideal obfuscation in the pseudo-random oracle model. So this is not in the plain model. And in fact, the pseudo-random oracle model can be heuristically instantiated by a hash function. So in other words, you get some security guarantees that you would expect from ideal obfuscation, which is simply you imagine all the parties having oracle input-output query oracle access to this function. So this is a very strong form of obfuscation. And ideal obfuscation actually applies even more cryptographic primitives. I'm not going to list them, but there's a lot. And it provides meaningful security guarantees even for things such as machine learning models. So as an example, imagine we have ChatGPT 23, which is a personal assistant that you carry around in your pocket. And it's your mental health, it's your whatever advisor, and it knows all your deepest and darkest secrets. If you were to lose it or someone were to take this device, the ideal obfuscated version could be tortured and yet reveal nothing beyond just the input-output behavior. And there was a long line of works attempting to put I/O on solid foundations, and this really culminated in the work by Jain, Lin, Sahai in 2020, where they show that using a long line of works, you can actually get I/O from these 4 assumptions. And they later followed this up by removing the need for LWE. Unfortunately, one of these assumptions, D-lin over bilinear groups, plays a very central role in the construction, and it's quantum broken by Shor's algorithm. And so we'd really like to get some sort of post-quantum I/O, and there's been a lot of work on plausibly post-quantum constructions. There have been works from multilinear maps, tensor products, noisy linear functional encryption, affine determinate programs, and the split FHE paradigm. And in many of these works, the problem here is that there's no reduction to simple falsifiable assumptions. And there's these 2 works later that instantiated the split FHE paradigm. One was by Gay and Pass 2020, and a follow-up by the same authors on the Gay and Pass paper, which was this shielded randomness leakage assumption. And here we have a circuit-dependent hardness assumption. So each circuit being obfuscated actually gives a different hardness assumption. This makes it very difficult to cryptanalyze. And in fact, this assumption has an explicit counterexample given to it by Hopkins et al. In 2021. And this is not an attack on the obfuscation scheme, just an attack on the assumption. Similarly, Wicks in 2020 introduced this homomorphic pseudo-random LWE sample assumption. And here in their assumption, they had an unspecified circuit implementation of a PRF. And again, this was exploited given attack by Hopkins et al. In 2021. And again, this is not an attack on the obfuscation scheme they present, just on the assumption. And when you do specify such said circuit for the PRF, it becomes difficult to explicitly write down the error distribution. And as a result, it's very hard to cryptanalyze. So we have all these really beautiful post-quantum I/O candidate constructions, And what we would really like to do is use cryptanalysis as a tool to refine our assumption and to understand the security of these assumptions. And therefore, when we construct these post-quantum I/O candidates, we actually need to make sure that we're able to facilitate cryptanalysis. And the desiderata for such assumptions is 1, simple to state, 2, falsifiable, and 3, all parameters and circuits should be fully specified. And towards this goal, the work of DeVatis et al. In 2021 presented a candidate construction for post-quantum I/O whose security follows from something they introduced called the subspace flooding assumption. And this is the first fully specified and falsifiable assumption. All the circuits and parameters are fully specified, and it's falsifiable. The candidate construction is rather elegant, and they also provide thorough cryptanalysis where they show that prior attacks such as rank attacks, sum of square attacks, these all fail. And let me just flash the subspace flooding assumption real quick. You don't need to understand all the details. I will just pick apart the parts that are important. But you have effectively a bunch of matrices drawn from some distribution that hides this bit B, which I highlight in green. And the seed B star, is a way of generating a pseudo-random LWE sample from a smaller, expanding from a smaller number of bits to a larger, or you can think of smaller matrices to a larger LWE matrix, or pseudo-random LWE matrix. And critically, the security property here is that this error that you get from expanding from a small seed to a pseudo-random LWE error should be able to drown out a specific error distribution. So this is falsifiable because it's a specific error distribution. And this specific error distribution you see here is E_G inverse B hat of minus B times F, where I'm not going to specify what any of these are, but and I'm happy to answer any questions later. So what does our work do? Our work shows the following theorem, informally. Under reasonable conjecture, when the bit is equal to 0, there actually exists a full break where there's a PPT algorithm that recovers all the errors EI from the seed. And as a corollary, under heuristic argument, we obtain a PPT distinguisher for the subspace flooding assumption. And let me describe to you what the conjecture is. It's very mild. Suppose you have T many linearly independent vectors, and I left multiply all these vectors by some matrix P whose height is much larger than the number of vectors. Then the conjecture is that these vectors remain linearly independent. And what is this matrix P? This matrix P has entries drawn from some LWE error distribution, say a discrete Gaussian. And this is in fact provable if you take the entries of P from a uniform distribution or a small bounded uniform distribution. Okay, so let me motivate the DQVWW21 construction approach. The work of Lin et al. In 2016 showed that any non-trivial compression of the truth table is enough to imply I/O, and that's what they called XIO. And it's not hard to see that that another notion named succinct randomized encodings implies XIO, which implies I/O. Therefore, to build I/O, it suffices to build what we call succinct randomized encodings. And what is a succinct randomized encoding? It simply takes a function f that takes L bits to capital N bits and produces encoding that takes in the description of f and an input x. And from this encoding, you can recover f of x, that's correctness. And security says that if I take two inputs, x0 and x1, who evaluate identically under f, their encodings are computationally indistinguishable. And for this notion to be non-trivial, because otherwise you can make the encoding f of x itself, you just need some compression on the encoding. The length of the encoding better be smaller than the length of the output of the function. And they construct this encoding scheme, and you don't need to know the details here, but I'm just going to highlight one part of this encoding scheme. So this encoding scheme takes the description of f, an input x, draws a random matrix A, produces a homomorphic commitment to x using this. It's actually a pseudo-random matrix A, but I'm going to gloss over this fact. And you can think of this, if you're familiar with dual GSW, this is some dual GSW-based homomorphic commitment to x. And then you're going to have some trapdoor, this post-evaluation randomness that will allow you to recover f of x from the evaluation of the commitment. And you're going to smudge this post-evaluation randomness with some pseudo-random matrix. It's not really a random matrix. This is some flooding matrix. And what is how are A and S star related to this seed B star? Well, seed B star can be used to generate a pseudo-random LWE sample of the form B star equals AS star plus E star. And a critical question that we ask is, how do you generate a large pseudo-random LWE sample of this form from a small seed? Okay, so you're going to take something that's rather short, and you want to generate something that looks like A times S star plus E star, where A and S star look random, uniform random, and E star has something that looks something like a discrete Gaussian or some LWE-friendly error distribution. And a natural approach that DQVWW21 takes is tensoring. Suppose that the seed B star just consists of two LWE matrices. One is B1 and one is B2, and each of them of the form AI, SI plus EI. Well, a natural way to generate a larger LWE sample is to just smash them together with a tensor. And by the mixed product property of tensors, you actually get this nice relation that we can have this block matrix A star, this block matrix S star, and the new error will just be E1 tensor E2. And our attack critically exploits this tensoring operation, and I'm going to provide you just some intuition about why tensor operations do not work well for producing larger LWE samples. And this is a heavily watered down version of our attack, but I think it will provide some intuition for the vulnerabilities that you incur when you use tensoring operations. So suppose we knew A star times S star, I'm going to call this Y. The question I ask is, do the secrets in the seed remain hidden, so S1 and S2? And I'm going to highlight in orange the known values. And suppose, in any good LWE assumption, you knew A1 and A2. Well, then I claim that you can actually recover S1. And how do you do that? Well, if you knew A1 and A2, you can just compute a left annihilator of A1 and A2. Think of A1 and A2 as tall matrices. And what I can do is I can multiply both the left-hand sides, both the left-hand and right-hand side by the M by M identity matrix, don't worry about the M, tensored A2 perp. And what happens? This A2 perp is going to kill off the second block. So when I expand this block matrix multiplication, I get the following equation. I just get some known values as equal to some linear, we basically just get an affine system of equations and the unknowns, which are V1. And we can actually recover S1 just by directly solving an affine system of equations. So this is how you would recover, for example, S1. So let's say we know S1 now. Then, since we know B1 and we knew A1, we can recover E1. And if I know E1, I can go back to the top and now repeat for S2. And the big question is, if I knew all these values, we'd be able to recover the error terms and the secrets in the seed. But the construction they give actually does not give out A1 and A2. And it obviously doesn't give out A star, S star, because otherwise you would know E star. So here's an intended attack, just a hypothetical outline. We would like to recover A1, A2 somehow because we are given A star, which is some matrix that's a function of A1, A2. A star is this thing that you see here, A1 tensor identity, identity tensor A2. We would then like to compute somehow using the givens in the subspace flooding assumption, y equals A star times S star. We won't be able to, but that would be the ideal. And then we'd recover S1 and then repeat for the next index. So this is the ideal approach to this attack. And suppose you had A star, and A star is equal to some U1 tensor identity, some A1 tensor identity, identity tensor A2. I'm going to call I'm going to rename them U's because they're going to be unknowns. And the question I'm going to ask is, can you recover the components A1 and A2 from A star? Okay? And this is your equation set. And of course, you have hypothetical constraints made by the seed, but you don't know the errors, so you don't really know these constraints. And the first problem is that there are actually many possible solutions. And we actually need a unique solution in order for our attack to work. What's a possible solution? Well, a possible solution for U1 is just A1. And the corresponding V1 solution for the secret is just S1. But obviously, you could just multiply A1 by any invertible transformation T, and S1 by T inverse, And this would also be a possible solution. So you actually have tons of solutions. And how do we make unique search possible? Well, we're going to break A1 into its top square block and a bottom rectangular block, and pick T to be the inverse of the top block. So in other words, for uniqueness, we're going to insist on a solution of the form where the top block is the identity. And actually, this is the intended solution, of course, is the one I just showed you. And in fact, this is enough to prove uniqueness. This enables a linear independence argument made possible by both this form of the solution and by tensoring. So suppose you recovered now A1, A2 up to unique representation. The question is, how do you get this Y? Well, from the givens in the pseudo-random, in the subspace flooding assumption, you can actually compute something that almost looks like A star S star. It's this Y prime equals A star S star plus RG inverse B hat. G is a gadget matrix, B hat you can just think of as a homomorphic commitment to 0. And you know B hat. So since you know G inverse and you know B hat, you can actually compute a right annihilator for G inverse B hat. The shape of these matrices work out. Multiply by Q on both sides. And you get something of the form Y equals A star S star times Q, where you know Y and you know Q. And you know A star. Great. And finally, how do we recover S1 from this? Well, here's the equation written up again. Here you have Y, you know A star, which is this block matrix. And then you have S star and Z here I'm just smashing S1 tensor E1 together, and you know Q. So what are you going to do? You're going to rewrite this equation simply as Y double prime A double prime times X1, where X1 is just V1 in a vector format, plus B double prime, where X2 is Z in a vector format. And you would like to show uniqueness. And to show uniqueness of this, it suffices to analyze the overlap in the column span between A double prime and B double prime. And it actually works out because of this tensoring operation that you can actually show uniqueness using this column span overlap technique. OK, final remarks, my last slide. Actually, I heavily watered it down. There's a lot of randomization tricks that are being used on this A star. Namely, they include these matrices P and P prime to to help randomize A star, as well as applying Killian randomization on this A star. And actually, this P and P prime, the conjecture I showed you, makes our toy example, our toy attack actually extend to the presence of P and P prime under this reasonable conjecture I showed you earlier. And also, using a column span argument, you can actually show that Killian randomization on this A star and S star do not hide the tensor structure. So this could be of independent interest. And finally, we show that the attack extends to a T-sum candidate presented by DQVWW 2021. Namely, if you sum up a bunch of these tensor constructions, it's no more secure against this attack. And that's it. Thank you very much.
So we have time for questions.
Hi, thanks for the nice talk. So, I think what you showed is that this operation of compressing, LWE samples using tensoring, this does not work, right? So, does your work give insight as to, ways that are less structured than tensoring that could help out?
Right, so effectively what you can think of this is an attack on the secret of the tensoring. Okay. And what you really need is a way to somehow obscure the secret. So previous work, for example, Hopkins et al. 2021, actually attacked the error, E star, directly. And there, basically, when DQVWW 2021 came along, their construction ideas really prevented against E star.
I remember that.
And so when you generate, basically the takeaway is if you want to have some sort of expansion, you need to also protect the secret somehow.
Sure, but I mean, does your work offer any insight as to
No,
how?
but we do have an idea that we are working on to patch
great.
it.
I look forward to seeing that.
Yes.
Thanks.
Thank you.
Any other questions? I have one. So you had this conjecture, believable one, which was simple to state, I guess, using LWE noise.
Yeah.
Which did you actually try to test it?
Yeah, so testing it even works on square matrices. Like and we have something that's very, very like wide. So it should be even more believable. We tested in Magma. We also have code for this attack in Magma. So this attack actually is implementable for small parameter settings. The tensoring makes it absolutely nuts to like actually implement in large.
For an attack, probably you won't even care if it's really proved because it's working anyway.
Yes.
Okay. Okay, any other questions? So let's thank the speaker and the other speaker, both of the session. I guess all the speakers of Eurocrypt, and see you next year.